All right, good morning to all. Um, Today we're going to recapture the chapter 6 that we discussed the week before the long weekend power flow analysis using Newton-Raphson method. But we did cover this topic a week before, but there are some slight changes. So to quickly I have to discuss the amendments in this chapter. So as we spoke the previous section, this is a content. Basically, we discussing about the load flow using Newton-Raphson method. But in order to understand the load flow, the first step you need to formulate the Y-bus equation, and then after formulating the Y-bus equation, we need to mathematically derive the power flow equation for the load flow. And once these two are done, the next step we can directly apply the Newton-Raphson method to solve the power flow problem. And we had an example of a 3-bus power system which is solved, and the solutions are given, step-by-step solutions are given for the power flow using Newton-Raphson method. And the end of the section, we should have a tutorial problem that can able to assist you for further understanding of the Newton-Raphson method. But there was a solution for the tutorial, but of course the steps of the problem to be solved by yourself in order to verify the solution that is given in the presentation. Right. If you have something on your hand on your side, please let me know because I can't able to see it. If you have any queries during my presentation, you can just raise up your hand so that I can able to see from the blackboard and I able to answer your queries. So in theoretically principle, we discussed about the introduction section. The slides are not moving. Okay, just give me 1 minute because I can see from the blackboard and this environment, the slides are not moving quickly.
You too. Jesus, look at this. This is full of lens line. Exactly.
Okay, can you able to mute your side, please? Unless if
What's the
you
point
have
of
any
writing here
queries.
when you
Everybody, can you please mute on your side? Otherwise, I should force to mute you.
Mr. Mr. Cindy, limit your mic, please. Mr. Cindy Lay.
Okay, let me unshare and share again. Just 1 second. Okay, I believe the slides is moving on your side. I'm on the blackboard, I can control it. Let me start from here. Okay, so as we spoke in the previous section, the load flow that is used for understanding the operation and planning aspect of the power system. And you can see there is a 3-bus power system that is given in the SLD diagram, and this is exact network model that we modeled in the MATLAB simulation. And today also we're going to model this network in the Dixieland and do the same load flow and even compare the load flow results of the MATLAB versus the Dixieland as well. So, but there are a lot of methods available to solve the Newton-Raphson load flow. Sorry for using the load flow method. One of them is a Newton-Raphson, and the second one you should have a Gauss-Seidel and fast decouple method. But mostly the preferable method by all the software they're using a Newton-Raphson method. So for this course, we stick to follow the Newton-Raphson method of the load flow analysis. And I think we did discuss about the Y-bus formation. As we see in here on the left side of the picture, you have a 3-bus power system, exactly the SLD diagram that we seen in the previous slide. There is a source impedance that is acting on all the 3 buses, and there is a shunt capacitors that is connected, which is denoted as Y02 SH divided by 2. In all the branches, the shunt capacitors is added, and there is also a series. There is a shunt capacitor actually added on the sending end and receiving end of the line as well. So we did discuss about this thing in order to formulation the Y bus matrix. So we discussed and we formulated the Y bus. So in order to find out what is Y11, which is a self admittance connected at bus 1, and Y22 is a self admittance connected as bus 2, and then the Y33 which is a self admittance connected as bus 3. And the resultant equation is given here, which is basically half of the shunt reactance that is connected on the each buses. Unless if you need a details, we can go on to discuss about the Y-bus formation, but it's a kind of repetition that we did last time. I do believe and hope that you understand how we formulated the Y-bus equation. And then we are applying a KCL, which is a Kirchhoff's current law, to bus 1, which is bus 1 is here. If I have highlighter here, so if you look at this is your bus 1, and we are applying a KCL at bus 1, which is I1 equal to the current that is flowing into the network, which is I11, because I1 is the incoming current, which having a 3 current that is flowing into the network, which is your I11 plus I12 plus I13. So it means I12 is the one that is flowing through this branch, and I13, which is the one that is flowing into this branch, and I11, it is a self-admittance current that flowing into the branch. So summation of all these currents will give you, you substitute the equation, but basically it's a Kirchhoff's current law. So for I11, we can apply a Ohm's law, that is current equal to voltage times of admittance. And the same thing you did for I12 and I13. And finally, we having an equation that is derived, which is I1 equal to V1 Y11 plus V2 Y12 and V3 Y13. And the same principle you apply for Kirchhoff's current law for node 2 and node 3 as well. And finally, you determine what is the Y-bus matrix for the given power system network. For in this case, you can see it here, the capital Y11, which is equal to Y11 plus Y12 plus Y13, and the small y12, which is this one, capital Y12, which is the line admittance between line 1 and 2, which is equal to minus negative of admittance connected between the branch 1 and 2, which is Y12, and Y13, which is admittance between 1 and 3, which is this node coming 1 and 3, and which is a negative of the admittance that is connected on the branch, which is small y13. So we discussed this thing. So I believe you should able to understand the formation of the Y-bus equation. Finally, when you apply the KCL for bus 2 and bus 3, and we getting I2 and I3, and then we can write this based on the KCL equation for the 3-bus system. We can write the total current I1, I2, I3, which is equal to its equivalent admittance times of the voltage, the admittance matrix, which is called as Y-bus matrix. So in simplified form, we can write your IA equal to Y-bus matrix times of VI. So this is for the 3-bus system, but in N-bus system, we can generalize the equation in terms of IA equal to Y-bus times of VI. And in summary, for N-bus system, we can say your IA equal to summation j equal to 1 to N, which is Yij times of Vj, which is N is nothing but, which is nth buses, because we can have bus 1, bus 2, bus 3. But in the typical example, we consider as a 3-bus matrix, a 3-bus network. But in complex power system, the number of buses in the system can be n. It could be a 5 bus, 10 bus, 20 bus, etc. So we can write in general formula for the KCL, applying the KCL formula for any network, we can write the complex for IA equal to summation of j equal to 1 to n, which is the Yij times of Vj. And then some observation we found out from the Y-bus matrix that is also we discussed, but I'm not going to go into details of the Y-bus. The points that we can discuss few things is the Y-bus is a spare matrix, and also we spoke about the diagonal elements are dominating, off diagonal elements are symmetric. Symmetric means if you have a determinant of any, if you have a determinant of A, and the transfer function, the transfer of the determinant A transfer, which is equal to A, then we called as a symmetric, because your Y-bus matrix you form mating, which is a symmetric matrix basically. And then the diagonal elements of the each node is a sum of the admittance. For example, we see from the previous slide the diagonal elements, which is a summation of y11, y12, and y3. That's what they're speaking. The diagonal element of each node is a sum of the admittance connected to it. The off diagonal elements, it will be the negative of the admittance, which is also we seen in the previous slide. So these are some of the observation from the Y-bus matrix. Before I move on to the next step, which is the mathematical formulation of the power flow. From the flow, if you have any queries on the Y-bus matrix, I think it's just a recap that we're doing from the last week. But if you have any queries on Y-bus matrix, you can able to put up your hands so that we can clarify it before I move on to the next section. So I don't see any hands. So it means I believe the Y-bus matrix formulation is clear to everyone. Okay, let me move on to the next section. We are on slide number 6. Let me move to 7. Okay. See the load flow equations for that network. We want to discuss the general load flow equations for any power system. Basically, the complex power injected by the source into the bus I of the power system, which is the complex power, can denote as equation number 1, which is SI equal to PI plus J times of QI, and which we can write also Vi times of complex conjugate of II, which is in equation number 1, which is representing the complex power Si, where I is equal to 1 to n. And then for convenient purpose, instead of we can write II, okay, II conjugate, we can remove the conjugate, we can write a complex power II. In order to take a complex conjugate, so we have to take the complex conjugate of the equation. So it means the P plus Ji, when you take a complex conjugate, we have P minus JQi, which is equal to, that's why we're taking the complex conjugate. You can see the V having a star, but I, it's a conjugate complicate if we take it and we denote as I, because it is easy to represent the current instead of instead of writing in a complex current, instead of writing in a conjugate current. So first equation 1, if we take a complex conjugate, we can write Pi minus JQi, which is equal to Vi star times of Ia, which is 2. So basically equation 1 and 2 is the same, but the only thing is in equation 1, when you take a complex conjugate, it formation as equation 2. And then what you're doing is substituting the value of II in equation 2. So what is II? From the previous step, when we formulating the Y-bus matrix, if you remember, we applying the KCL for the 3-bus system, and finally we wrote our n general equation by using the KCL formula for the 3-bus system, and we also represented for the n-bus system. But in that case, if you look at your II equal to summation of k equal to 1 to n yik times of vk. So this is what your KCL equation, bring it back, your generalized KCL equation for any power system network. Basically, your current is equal to what you're trying to say, your complex current, that is equal to admittance times of the voltage. That's what your KCL from the previous formulation of the Y-bus equation we derived. So we want to substitute this current II equation 3 into equation 2. So the left side is as it is Pi minus JQi. In your right hand side, where Vi conjugate is there, but instead of Ii, we replacing Ia equal to this equation number 3, which is summation k equal to 1 to n yik times of Vk. Is clear? The next step, we have to derive the load flow equation in a polar form, and we can able to substitute the voltage and magnitude, or maybe a phase angle, either in exponential form, a polar form, or rectangular form. Before going to pursue that, we can see this SLD diagram. In the SLD diagram, there is a bus I, is a sending end bus, and bus K is a receiving end bus. So the voltage across the bus I we can write as its voltage is Vi and its phase angle is delta I. And the receiving end bus K, the voltage for that bus is Vk and the phase angle we can write as delta K. So this is a line is connecting between bus I and bus K. So the current flowing into the bus, which is an II, which is what this IA is the one that we derived in equation number 3. And the admittance, okay, the admittance of the bus, which we can write as YIK angle of theta IK. So what we try to see is there is a sending end bus and the receiving end bus, and what is the phase voltage and the phase angle for the sending end bus, which is denoted as VI delta I, and for the receiving end bus is bus K, the voltage and the phase angle is denoted as Vk delta K, and the current is the one is flowing II, and the admittance of this line, which is Yik with respect to the angle theta Ik. So by bearing in this mind, we're going to write down the equation for Vi. Like you can see, as I mentioned in this statement here, if you read this one, we can write our voltage magnitude and the phase angle. Okay, the phase angle can be either in the exponential form, or it can be in the polar form, or it can be in the rectangular form. For example, your Vi, this is Vi is a Vi magnitude, and in exponential form we can write e power j delta I, and whereas in the polar form we can write this e power j delta I, we can write as phase angle delta I, and in the rectangle form the same delta I we can write as cos delta I plus j sin delta I. Is it clear how we can write the Vi magnitude, especially the phase angle? The phase angle can be represented in exponential form, or it can be represented in a polar form, or it can be represented in the rectangular form, which cos delta I plus j delta I. The same thing applies for the Vj. Okay, for Vj we can write Vj exponential of E delta j, and you can write in exponential form the phase angle Vj delta j, or you can write in terms of the polar form cos delta j and sin delta j. So then we coming back to your admittance of the line, the line which is Yik and the angle of theta Ik, and this theta Ik, which is a phase angle, but we can write this phase angle in terms of exponential form, or you can write in terms of the polar form. So that's what we can see. The magnitude Vik is as it is, and each angle is written in exponential form e power j theta Ik, and the next you can write the same angle E j theta Ik can be represented as angle of theta Ik, and it can be represented in a polar form in terms of cos of theta Ik plus j sin of theta Ik. I can stop now to ask you if you have any questions. Are we writing the voltage magnitude in terms of the three forms? The phase angle, the phase angle. Are we writing the phase angle in exponential form, polar form, and rectangular form? Any queries from your side? If you have any queries on how we writing the phase angle in exponential form, polar form, and rectangular form, you can please clarify. If not, then I will continue. All right, I don't see any questions from your side, so I can continue. So by observation of that equation, so we can write like example the equation 4, which is Pi minus JQi, which is equal to Vi star summation of k equal to 1 to n Yik and Vk. So this equation is written only in terms of the magnitude, not with respect to the phase angle. So the equation 4 can be represented again here in equation 5, but only thing what you're doing is we're bringing back our phase angles with respect to equation 4 into equation 5. So the left side Pi minus JQi as it is, and the right hand side you can say is a V conjugate. So what we can write is in V conjugate Vi minus delta I. Can you understand why is delta I? Because it's a V conjugate, Vi conjugate. So for that we introducing a minus delta I. And then within the summation block k equal to 1 to n and Yik, and you can see the Yik, the phase angle is theta Ik. If you remember here from this case Yik, the phase angle is theta ik in polar form, so we writing in theta ik, and Vk as it is, and the phase angle in polar form Vk, which is a delta k. So what we're trying to do in equation 4 and equation 5, equation 4 is as it is, equation 5, we expanding equation 4 with respect to introducing the phase angle phase shift of the voltage component and also the admittance component. The phase angles is represented in this equation in polar form. All right. From this equation 5, in the next step, we can see the phase shift between delta I minus delta K, which we can write as delta Ik. Example A, you can see minus delta I and A is delta K. So if you multiplying delta I minus delta K, which we can write delta I delta K, which is equal to delta I minus delta K. So from that equation, we simplify again highlighter. But are you not able to see the and that I'm using here? You can't able to see this some type of arrow mark that I'm using here. Can everybody can confirm, can you able to see the highlighter that I'm using here? As
We
a
can
kind of
see now, so it's blue one. Yeah.
Okay. Sometimes I'm not sure if there is a network delay from your side, you know. All right. So what we're trying to do from equation 5, so we write delta I minus delta K, which is right delta I minus delta K, which can be represented delta Ik. So what we do, we simplify this equation 5 with respect to this formation. So the left hand side as it is Pi minus JQi, which is equal to summation K equal to 1 to N. And here if you look at it, what are the magnitude Vi, Vk and Yik. So you can see Vi, Vk and Yik. Vi is the voltage at the sending end and Vk is the voltage at the receiving end bus, and Yik is the admittance of this line, which is the phase angle in the polar form for all of them. So we remember Vi, what is the Vi, the phase angle is minus delta I and Vk is delta K. So we wrote already Vi delta I minus delta K can be written as delta Ik. So what we're trying to do, that's why because of the complex conjugate, we have minus of delta Ik and then the angle for the Yik, which is minus theta Ik. Is it clear? So the phase angle for this entire unit can be written as minus delta Ik minus theta Ik. And where this minus is coming? Because of the complex conjugate of the VIA, this minus delta that is representing here. Then the next step what we're doing is, so we write this thing in the polar form. Okay, so equation 6 is written your complex power into your polar form. Now in equation 7, that is the next step what we're doing is we writing this equation 6 in a rectangular form. In rectangular form, what will happen? The delta can be represented, because if you remember the rectangular form, we're going to introduce your cos term and sine term. Okay, like here what I'm highlighting here. So in this equation, we're going to change this phase angle phase shift of the in polar form into a rectangular form. So when you're changing to a rectangular form, we're introducing the cos term and sine term. So as it is, the equation 6 is written left side, there is no change, and the right hand side you can see the Vi, Vk, Yik is there. But this phase shift, whenever the phase shift is coming, we are writing this phase shift in a polar form, sorry, in a rectangular form. This polar form can be converted into a rectangular form. When we're converting in a rectangular form, you can see which is a cos of minus delta I k minus theta I k and minus j sine of delta I k minus theta I k. So then now we have to equate this equation in terms of, we separate this equation real power and imaginary power. The real power is Pi, the imaginary power is Qi. So for the real power, this first term, the cos term is coming in. So it means you have Vi is a constant that taking out, and Vk, Yik cos of theta ik minus delta ik, because this minus is operating here. If you operate this minus minus become plus, and delta ik is minus. So that's why theta ik minus delta ik, which is represented as the real power in equation number 7. And equation number 8, we are representing a reactive power. So the reactive power Qi, which is equal to, you can see there is already one negative sign is there. So we taking that negative sign. So Vi is a constant minus Vi, summation of k equal to 1 to n, and Vk Yik sine of theta ik minus delta ik, which is representing the reactive power in equation 8. So equation 7 and 8, which is representing the real power and reactive power of the power system. Okay, I should just open up the floor now to see if you have any queries, how we come up with the equation 7 and 8. Is it clear? Because equation 7 and 8 is a very important equation. We're going to derive the rest of the step, like formation of the Jacobian matrix, in order to solve the Newton-Raphson load flow using equation 7 and 8. So it is basically to understand equation 7 and 8. That's what in the updated slide I managed to put your equivalent system network, which representing your sending and receiving end bus, and the power flow is going, and also bringing back into the concept of how we can represent your phase angle in exponential form, in polar form, or rectangular form, so that the detailed version will give much better understanding how we come up with equation 7 and 8. No question from at your end. Okay. Then I should move on to the next slide. So this slide, actually I can skip this slide because there is a two version you can derive the equations 7 and 8, but it's the same procedure. But as I mentioned here in the top of the slide, is alternative method of deriving the real and reactive power for the system. But I can quickly run through it. But obviously your previous slide number 7 and 8 is the same, but only thing is alternate way of we can derive your real and reactive power of the power system. So as we know from the previous cases, your complex power is represented as SI equal to PI plus JQI, and which can be represented VI complex IJ. Okay, and then here you're substituting from the KCL your IJ equal to K, IJ equal to from equation 3. So there is nothing change up to here. And the second case, if you look at here, the phase angles will be represented in a polar form Vi delta I, and your receiving end bus Vk delta K, and then the admittance of the line connecting is the same as it is what we discussed on the previous slide. The magnitude is Yik and the phase angle is theta ik. So we again substituting equation 3 in equation 2, and we getting back to this equation. From this equation, we can directly replace your imaginary part, real and imaginary part, because you from this equation, instead of we taking delta I minus delta K, we can just use the real part of, you can see here the real part of your Vi conjugate times of K equal to 1 Vkij, and for complex power we can take minus imaginary part of, again the same equation what you wrote, Vi conjugate times of summation K equal to 1 to n Yk times of Vk of Yik. And from this equation, like earlier slide I spoke about, your Vi can be written as Vi delta I, and Vk written as Vk delta K, Yik will written as Yik and theta Ik. This is written in polar form, or either you can write them in a exponential form, or you can write them into the rectangular form as well, as we discussed in the previous slide. So what we're trying to do now, for the real power, you can see the equation 5. Okay, here we bring in the equation 5, that is the Vi is a summation K equal to 1, and then Vk Yik cos. But what we're trying to do, this the phase angle, phase shift for Vi, which is minus delta I. You can see the minus delta I, and Vk is delta K, and Yik is theta Ik. So we can write from this equation 5 as it is theta Ik plus delta K minus delta I. And for the second equation, this negative sign as it is, And again for Vi, we can write minus delta I and Vk delta k, and for the Yik, the phase shift is theta Ik. So basically, we can formulate 7 and 8 as we spoke on the previous slide. Is the same procedure to derive equation 7 and 8, which is representing the real power and reactive power. For better understanding, I am providing two methods which we can derive your real and reactive power of any power system by using this simple system, which is a sending and receiving end bus, which is represented as bus I and bus K. Any questions from this slide? There is no questions, I can move on. So the next slide, sometimes, as I mentioned in the previous lecture, sometimes the power flow equation can be represented in terms of using rectangular form, or maybe they using in exponential form. So that's why they have a different equation here, your Pi and Qj. But what they're trying to do, they're using instead of a polar form, they're using a rectangular form to represent this thing. But we're not going to consider this one, because in our approach we're using the polar form for the entire section of the Newton-Raphson load flow. But I just want to bring it to your attention, because if you're referring some other textbook, and some of the textbooks I am aware, they try to represent your real power and reactive power, which is given in 9 and 10. Instead of representing the phase angles in a rectangular form, sorry, in a polar form, they're representing into a rectangular form. Now we're coming back to the Newton-Raphson power flow method. Before we go into the mathematical formulation of the Newton-Raphson power flow method, so the Newton-Raphson power flow method is a common method that is used across the different platforms by industry vendors, and also the simulation platforms that are used by the different softwares. They also use the Newton-Raphson method, and few of the softwares you already aware of it, like example Power Simulator, SimScale, and Dixon and Power Factory. And there are other softwares that is also available in the market, which we're not going to use part of the courses, but for your knowledge, it could be a ETAP platform or RSCAD platform or PSCAD software. And those are the softwares that is also available in the market, which also using Newton-Raphson power flow method. And in some cases, you might see your Gauss-Seidel method must be used in some of the power flows. But the only advantage of the Gauss-Seidel method is it doesn't need a Jacobian matrix. When it doesn't need a Jacobian matrix, it means you don't need to require for the partial derivatives. But the disadvantages for the Gauss-Seidel method is it cannot able to solve a complex problem. But your Newton-Raphson, it does not depends upon the complex of the system. The complex of the system can be determined by using the number of buses that is connected in the network. So for Gauss-Seidel method will be good if the network is a simple network with minimum number of buses, whereas Newton-Raphson method can be applied from small scale to large scale system. That is advantages. And also we spoke about the Newton-Raphson solution will always be very close to the final solution if our initial guess are pretty much close to the final solution. Otherwise, you should go for a more number of iteration. Instead of a few iteration, you can get the solution. And the disadvantages point of it, it mentioned again, the each iteration takes longer than the Gauss-Seidel iteration. The reason for that I already explained to you, because for Newton-Raphson, every iteration it have to determine the Jacobian matrix, and when you determine the Jacobian matrix, then you can able to calculate what is the change in real power and reactive power, and it check with the convergence with the mismatch power flow, and if the mismatch power flow within the tolerance limit, it will able to converge. So because of every iteration, it have to take a Jacobian matrix. Obviously, the computation time must be higher than the Gauss-Seidel method. But again, as I mentioned a few weeks ago, due to the embedded system technology now, there are different embedded system technology which have a very good processors are available in the market. Due to that, the computations and memory aspect of the computations is not an issue at all. So that we can able to still use the Newton-Raphson method to solve any complex power system problem. Even it is a small network, medium network, or large network, the Newton-Raphson capable able to solve the power flow. As some of the theories on this Newton-Raphson method. Followed by that, again, some more theoretical notes is coming for the Newton-Raphson method. In the first point of this one is speaking about Newton-Raphson method needs less number of iteration to reach convergence, but it takes less computer time, hence the computation cost is less and convergence is certainty is said. And Newton-Raphson method is more accurate. This is what I mentioned, and is insensitive to factors like slack bus selection, regulating transformers, and etc. If you remember last week when we were speaking about the Newton-Raphson method, the slack bus is not taken into account, but whereas in Gauss-Seidel, the slack bus is taken into account. So, and then these other cases, sometimes we have a regulating transformers and etc. So that won't influence anything in the Newton-Raphson method. The drawback of this method are difficult solution technique because each iteration need a large computer time iteration. But again, this memory problem is not a deal nowadays due to the compact storage scheme that is available. I pretty much sure you know the physical hard drive and also the SSD. SSD is a solid state drive. So nowadays you can see like a pen drive type of size which you can have your memory so that it can be replaced with your hard drive with the SSD drive, and the computation performance and the memory for the computation will be good compared to the previous technology that is used in all the PCs. And then the Newton-Raphson method can be applied to the solution of the power flow when the bus voltages are expressed in polar form. You remember I spoke the Newton-Raphson method, we need to express the bus voltages in a polar form, not in rectangular form. And only polar form is used in practice because the use of polar form results in a smaller number of equations than the total number of equations in a rectangular form. These are some of the theories of the Newton-Raphson. Okay, the next slide, we coming to formulate your Jacobian matrix based on the real and reactive power equation that we derived in a couple of slides ago, which is represented by equation 7 and 8. Okay, so if you remember equation 7, this is what your equation 7 is written. But what we're trying to do, we extend this equation in terms of k is equal to I and k is not equal to I. So from this equation, if you represent k is equal to I, we can write the first term k equal to I means, it means your Vk become Vi. Excuse me. I think if you write this equation, I just write this term, but here I written k is equal to I, k is equal to I to n. And the second term I written as it is, but here I wrote k is equal to 1 and k is not equal to I. Can you able to see your equation 7, which is represented by Pi, but only thing is in the summation form, I wrote k is equal to I and k is equal to not I. So I'm just equating this equation into two terms. The first term here, which is k is equal to I, and the second term here, k is equal to not k not k is not equal to I, where k is equal to 1. Then what I'm doing, I'm applying k is equal to I. When I apply k is equal to I, for Vk in terms of Vi and Yik in terms of Yii, and here the cos of theta ik, it become the k is become cos theta ii plus delta I minus this delta I is as it is. So it means is plus delta I and minus delta I will cancel each other. So in the result, I can write this equation. If I apply k equal to I can write Vi times of Vi times of Yii cos of theta ii plus the second equation. Second equation you write as it is because where k is not equal to I, k equal to 1 to n. And in summary, we can write I is equal to 1 to n, where bus 1 is a slack bus, for k is equal to 1 to n as well. The same equation, the same thing will be applied for the reactive power as well. In reactive power equation, which we derived a couple of slides ago, which is represented as equation 8. This is equation 8, and we're writing exactly as it is equation 8. And then what you're doing is, again, this term, we're going to write k is equal to I, and this term we're going to write k is equal to not equal to I, k is equal to 1. So from this equation, if you apply k equal to I, we again get instead of Vk we can write Vi, and Yik we can write Yi, and theta Ik, theta Ii, and delta I minus delta plus delta I minus delta I will cancel each other. So we get this term as it is. And this term we become Yii sine of theta I, and negative sign as it is, and this second term we written as it is. So what we're trying to do from 7 and 8 is the same what we represent couple of slides, but what we're trying to do, we equating this term in terms of when k is equal to I and k is equal to not I, then we can write a new equation for real power and reactive power, which is representing equation number 7a and 8a. So I just stop here. What we understand from 7 and 8, and what is the difference between 7a and 8a? 7 and 7a and 7 is exactly the same, but the only thing is we equating equation number 7 with respect to k equal to I and k is equal to not equal to I. And 8 and 8a is the same, the reactive power, but the only thing is in 8a we extended the equation 8 with respect to k equal to I and k is equal to not equal to I, so that we can finally write the equation 7 and 8 as 7a and 8a. Is it clear? Any questions with respect to 7a and 8a? Okay, if there is no queries, I can move on. So the next step, we have to formulate the Jacobian matrix. The Jacobian matrix is denoted by J, and which is a four-cornered matrix. Which what we can do is we're gonna partial derivation of the real power with respect to the delta and real power with respect to the V. Then the second case, we have to derive the reactive power with respect to the delta and reactive power with respect to the V. Then this will form as a four coordinate matrix J1, J2, J3, J4. So it means in the numerator, we deriving this real power with respect to partial derivation of delta and V. And the reactive power, we again partial derivation of delta and V. Which is slide number 12, 13 now. Okay, so from the previous slide, we know our 7a is written here and 8a is written here. But what we're trying to do with the help of 7a and 8a, we're going to find the elements of the Jacobian matrix. The first element of the Jacobian matrix J1, which means we're going to partial derivation of equation 7a with respect to delta k. So delta pi with the partial derivation with respect to delta k. When you derive this equation, we can see you derive with respect to delta k. So from here is a constant, okay? So this is not coming into picture, but here if you look at here, where is delta k? Delta k is here. Delta k is gonna be 1. So it means what you're trying to do, minus Vi, Vk, Yik, and this delta Ik, because it's a cos of delta. If you derive your partial derivation, your cos become your negative sign. That's why the negative is introduced, and sine of theta ik plus delta k minus delta I. Student, did you able to understand equation 11? Equation 11, what you're doing, we deriving partial derivative of pi with respect to delta k. And when you're doing the partial derivation of pi with delta k, so we just need to partial derivation of equation 7a with respect to delta k. And when you're doing that, in the first term there is no delta k, and this is a constant, it becomes 0. In the second term we have delta k. The delta k is cos of delta k, and the cos, if you do partial derivate, is a minus sign. So that's what you're looking at, minus Vi, Vk, Yik sine of theta ik plus delta k minus delta I, which is represented as equation 11. And the next one, we writing k is equal to, when k is equal to I, it means if you write k is equal to I, then we have to derive this equation, your 7a with respect to delta I. When you deriving with the delta I, you can see again in the first term there is no delta I, so this is going to be constant as 0. And in the second term we can see delta I. this is a negative cos minus delta I. So if you derive the cos, what will happen? Partial derivation of the cos is minus sign, and this delta minus delta will become minus, and this minus and the cos is going to be a minus sign. So it means that minus and this minus become plus. So that's what we can write as, this is k is equal to 1 to k equal to 1 to k equal to 1 and k is not equal to I. So we write this equation vi vk yik sine of, because the sign will be a minus cos, but this minus is become positive, then we can write sine of theta ik plus delta k minus delta I, which is equation number 12. Student, can you confirm, you understand how the partial derivation of pi with respect to delta I become equation 12? Okay, if you don't have queries, we can move on. So the next step, what you're doing, again we saying k is not equal to I. So k is not equal to I, we have to derive this equation 7a with respect to vk. And we derive by vk, and this term become going to be 0 because there is no vk involved. And here the vk is here, vk is 1. So what you're doing is vk 1 means, then we can say vi yik cos of theta ik plus delta ik minus delta I. And next, when k is not equal to I, when k is not equal to I, so it means when k is not equal to I, in that case, we want to derive by vi. So in this case, there is vi and there is a vi. This vi, we can write at 2vi. And the partial derivation of 2, the partial derivation of 2vi, okay? So it means is a vi squared. Vi is vi squared. So when you partial derivation of vi squared become 2vi. 2vi yi terms of cos delta I, and inside your vi become 1. So the rest of the term vk yik cos of theta ik plus delta k minus delta I, which is representing equation 14 when you partial derivative your pi with respect to vi. So do you have any doubts in equation 11, 12, 13, 14? Which is the partial derivation of pi with respect to delta k and delta I and delta vk and delta vi. Clear? Okay, then move on to the next right side of the slide, which is reactive power. The reactive power that we discussed on the previous slide, which is written 8a. So I just captured that equation as it is from the previous slide 8a. So what we're going to do, we're going to partial derivative reactive power qi with respect to delta k. The first case again, when k is not equal to I. When k is not equal to I, when k is not equal to I, so it means the first term is not going to be appear. So here we can delta k, this is delta k, this become 1, the sign of delta k. So sign of delta k, if you partial derivative sign, which is a cos. So what you're doing, we just this minus sign as it is, vi minus vi vk yik, cos of sign derivation is a cos of the inside function as it is coming. And then when k is equal to I, so when k is equal to I, again we partial derivation delta qi versus delta I. So in that case, we delta I is here, this one. So this delta I is negative. So its sign of minus delta I become cos of minus delta I. That's why there is a negative sign. So if you look at here, so the inside the summation sign, because this term will not coming in, this is 0, and this term, this sign of minus delta I become cos of delta I, and this minus become minus 1, and that minus and this minus become get positive. Minus minus is plus. That's what this equation is starting from plus. Summation k equal to 1 to I, vik, vi, vk, yik, and the sign term become cos, and the inside term theta ik delta k and minus delta I is there. Can you understand? The sign of minus delta will come cos of cos of this whole term, because sign of this term, but the delta we partial derivative. So this become sign become cos, but this negative become minus 1, and that negative and this negative become positive. That's why this term will be positive like this. And the next, we derive the partial derivation qi with respect to vk. And if you look at here, there is no vk in the first term, so this will be 0. In the second term, there is a Vk, and this Vk become 1, but there is a negative sign. So that negative sign is maintained. So Vi, summation Vi, then your this Vk become 1, and Yik, sine of theta ik plus delta k minus delta I, which is equation 17, when you partial derivation of your reactive power with respect to Vk. And the last Jacobian element, when k is equal to I in this equation, we have the diagonal element of J4, which we need to partial derivation of this 8a with respect to Vi. And a is the Vi become 1. So this means the Vi is Vi squared, and this Vi squared become minus 2ai. So minus 2 Vi yi times of sine theta I. I think student there is a small error I can see sine II, but it's supposed to be sine theta II. Theta is missing here. Please take note. I'll try to correct myself after the presentation. Theta is missing, sine theta II. Okay, the theta is missing. It's a typographical error. And then the inside, we again derive by partial derivation by Vi. Partial derivation by Vi, this become 1. So it means the inside term as it is, but the Vi become 1. So Vk Yik sine of theta ik plus delta k minus delta I. That is equation number 18. So basically equation 11, 12, 13, 14, 15, 16, 17, 18, which is a partial derivation of your real power with respect to delta and with respect to V. Then it will come to formulation of your Jacobian matrix. Any questions of how we formulating the elements of the Jacobian matrix? In equation, sorry, in slide number 13, which is denoted in equation 11 to 18. No doubt? All right. Okay, the next thing, we can solve one of the example by using the power flow equation by the concept that we discussed. I don't know if you need any break from your side. Or should I proceed? Students? Okay, it's 5 past 10. We can take 15 minutes break. I can stop recording.